Okay, so the problem, one of my favorites. So these are two cones. One has twice the dimensions of the other cone. So let me show you how I made the cones. So I printed out a circle and just cut out 1/4 of the circle. And then I taped this edge to that edge. Or in mathematician speak, I identified the edges, which now I know means I taped the edges together. And then you get a cone like that. So this cone and the other cone were cut out of the same sheet of paper, except this one has twice the linear dimensions in its circle. So I think this circle was 7 centimeters in radius, and this is 3.5 centimeters in radius. So other than that, they're the same. The question is, which one has the higher terminal velocity, or are they about comparable? So in particular, the question is this. So I'm going to drop them, and the question is, what's their ratio of their terminal velocities? So the ratio of the big cone's terminal velocity to the small cone's terminal velocity is equal to what? And you get choices along this axis. So here is okay, so those are the 5 regions to choose from. So you have 5 choices for the ratio, basically roughly 1/4. This is some range here, because nothing's exact, and we're certainly not going to do an exact experiment. Roughly 1/2, roughly 1, roughly 2, or roughly 4. Let's just get a straw poll, and then you'll have a chance to argue with your neighbor about it. So who votes for 1/4, which is that the, so let's see, 1, 2, 3, 4, 5, 6. Okay, 6. Who votes for 1/2? 2, 3, 4, 5, 6, 7, 8, 12. Who votes for C? About 22. Who votes for D? No takers. No takers for D. Okay. How about E? Okay. So now find a neighbor or two, 1 or 2 neighbors. Introduce yourself to your neighbor. And also, by the way, unless you're taking notes on your laptop, and really insist on doing that, if you could close your laptop, that would be very helpful for the purposes of discussion in this whole course. So find a neighbor or 2, introduce yourself. You'll be getting a chance to meet graduate students from across the Institute. It's a great opportunity. And try to convince them of your answer, especially if you have a different answer. Or if you happen to share an answer, well, see if you can figure out why you're sure of it. Or if you're not sure of it, see if you can settle that. Okay, so discussion time. 1, 2, 3. Okay, 4. 1/2. The halves don't have it. Oh, no, there's 1. Oh, there's 2. Okay, great. 3, 4, 5, 6. Equal. Okay, so that's about, let's call it 30. 2 and 4. Okay, so thanks for the votes. Let's take reasons for any of them. I'll take reasons for any of them. I'll put them up here. You don't even have to agree with the reasons. Just something you guys discussed and thought maybe was plausible. Yeah. For any of the reasons. So again, it doesn't have to be things you necessarily believe, but things that are plausible. And that's actually more instructive than what you think is for sure right, because you're trying to figure out what might be true, and you're expanding the ways you're thinking. Yeah.
C, because they have identical mass to surface area ratio.
Okay, C. So mass to area ratio is the same. Okay, can people think of plausible reasons against that argument? Yes?
I have no idea what the actual formula is for calculating.
Right.
If there was a square in there,
Mm-hmm.
then that would flip into a formula.
Right, so I'll call this not C. So suppose the formula actually depended on the square root of A or square of A or something like that. It's, say, 1 chance out of 3 that it has A to the first power here. It could have A to the 1/2 or A to the 2. So could be A to the K, M over A to the K for K not equal to 1. Okay, so let's do the experiment this way, which is that I will stand on the table and pray that I have matching socks on, which is sort of 80% these days. It's increased. And I will drop them on the count of 3. 1, see, are they both about the points about the same level? They look sort of to me, but my depth perception is actually quite bad. And yeah, there. Okay, so is that about equal? Okay, 1, 2, 3. Simultaneous. Okay, so there you have choice C. So now the interesting consequence of that, so what that shows is that drag in this case is proportional to area. I'm going to replace the proportional with a twiddle. So it has an area in it. So I'm just going to get something with the correct units now. So it has an area in it. And now you have left to play with density, speed, and viscosity. So now let's actually construct the drag force as a result of that. So we know by the experiment it's proportional to area. And now among these, so this here is the this is the kinematic viscosity, which is the one you may be more familiar with divided by rho, the density. So we got to put some of these guys in, some of these guys in, and some of these guys in, and make the units come out as a force. Well, one of them we can do right away. There's how many powers of mass over on this side? In a force, just one. Right, and there's none here yet. So we need to get 1 power of mass on this side. Now, among all these guys, which of them have mass in them? Not this one, because you divided it out. Not velocity. Only density. And density has 1 power of mass. So you have to put 1 density. Question?
I don't know what the units of drag are.
So this is a force. Good question. So drag is a force. So this is just newtons or mass length per time squared. Does that help? So it's just newtons in SI units, or in general, mass length per time squared. So a mass times an acceleration. Okay, so now we've matched the units of mass, but we haven't matched the units of time yet. So let's sort out the time. There's no time here. There's no time there. There's t to the minus 2 there. Well, what can we do about that? We have to throw in some v and some nu. And the problem is we don't know how much. So the time doesn't help us enough. Turns out, to make the time and the length work, the simultaneous constraint, the only way to do it is that. Okay, you make the same argument, just get the masses to match, the lengths to match, and the times to match. This is the only way to do it. So you don't have any viscosity. So actually that's the simplest experiment I know to show that the drag at high speed, in other words, most flows are actually high speed, high Reynolds number, is independent of speed, of viscosity. So it's rho a v squared. And that is a great result because it tells you all kinds of stuff about everyday flows in everyday life. Like, for example, why did people reduce the speed limit on the highway back in the 70s to conserve gas? Well, on the highway, you're burning gasoline to fight drag. So if you reduce the speed, you reduce the drag, you reduce the amount of gasoline. So in particular, if you reduce the speed by 20%, you reduce v squared by 40%, which reduces the drag by 40%. So you just decrease the gas consumption by about 40%. So you can see all these things right away just from this simple formula, which is an immediate consequence of this experiment.